One moment. All right, there we go. I think we're ready to go. 211. So we're here. Oops, not that. Okay. Want to extra parts? More extra parts. If there's any dying to know substitution questions, you just can't live without me addressing. If you happen to have something from section 6.1, you really need to ask about, you are welcome to ask. Look at my notes. That's not good. My notes. Sure, those notes. Have you talked about integration of parts at all in class yet? Okay, cool. Good. So just as a recap, here's what I would say about integration of parts. Sure. So integration of parts. So I would say first thing to note, you guys here, is most of the time, there's kind of one exception in this class. You really only use integration by parts for mixture integrals. When I say a mixture, I mean you've got two different types of things all put together. So typically a mixture of a logarithm and or an e to the x and or a trig and or x to a power. Those are kind of the four main types of mixture things that you look for when you're doing integration by parts. But I would also say when you see that, you only use this for mixture, and you should always first look for a U sub. So that's my two big words of advice when it comes to integration by parts, is it's not the first thing you should ever try, unless you absolutely know, like you've seen it before, you're like, yeah, I know it's integration by parts. If you're not sure, typically doing a U sub first or trying U sub first is kind of the better way to go. Just because we typically think of doing a U sub as the easier method of integration. That's always true, but it's kind of true. So, for example, you could be asked to do something like this. The integral of x times cosine of 5x squared. It's a mixture. I've got x to a power, x to the first, times cosine of 5x squared. And I have to ask myself, okay, what should I do? I'm going to think about a U sub first. Is there a good U sub here? Yeah, there is. We can let, or at least we can try, we can let u equal 5x squared. And then the derivative is going to be 10x dx. And oh yeah, that's going to work out all right because I have an x there. That x there is going to match up with that x there. It's going to work. And then we can do it the way your teacher likes to do it. Dx equals du divided by 10x. And then we rewrite this as x times cosine of u times dx, which is du over 10x. And then your leftover x's cancel out. So this just becomes the integral of, or say 1/10 the integral of cosine of u du, which is then just 1/10 sine of u plus c, which is then just 1/10 sine of 5x squared plus c. So, right, this is still qualifies as a mixture, but definitely is a U substitution, not integration by parts. On the other side of things, if someone said we want to integrate maybe x squared times cosine of x, This is looking a lot less like an integration, a U substitution problem. There really isn't a good choice for U here. Typically, you're looking to choose U inside another function. And we don't want to choose U equal to X, which is inside the cosine function. So U equal to X, definitely not a good choice for a U sub. So I'm thinking integration by parts. So let's see what integration by parts yields. All right, let's see. Gotta remember our acronym, late. So we don't have a logarithm, but we do have a power of X. So that's what I'm going to choose my U to equal, right? U is equal to, oh gosh, this is terrible. This is how we're choosing U. So I've got a power of X, so U is going to equal X squared. And my dV is the rest. So dV is going to be cosine of X times dx. All the rest, right, with the dx. The dV should always have a dx with it. The du should always have a dx with it. So du is going to be 2x dx. And v, the anti-derivative of cosine, is going to be positive sine of x. And then we have to remember the thing. What was the thing I said last time? Yeah, ultraviolet super voodoo. So, right, we're saying that this, so just as a reminder, right, what we're doing here is we're saying this is u, this is dv, and what we're saying is the integral of u dv is equal to the ultraviolet super voodoo. So specifically, the integral of x squared times cosine of x dx is equal to u times v. So x squared times sine of x minus the integral of v du, sine of x times 2x dx. Now, we've got a new integral to deal with. And although the integral does get easier typically if you're making the right choices for integration by parts, that doesn't mean it's always going to be straightforward. In this case here, we have to do integration by parts again. So I typically would prefer to make the choice of factoring out this 2 in front of the integral. Some people don't like to do that, but I would certainly choose to say that this is equal to x squared sine of x minus 2 times the integral of x times sine of x dx. You don't have to do that. You can totally leave the 2 in there. You could leave the 2 with the x and say your new u is going to be 2x. I'm going to say my new u is just x because that's, I don't know, it seems better to me. So u equals x. Typically, when you're doing repeated integration by parts, you make kind of the same choices, right? If you pick u to be a power of x in your first iteration, you're typically going to pick u to be a power of x in your second iteration. So u equals x. dv is the trig function, which is sine of x this time, dx. Du is equal to 1 times dx. And v is equal to the antiderivative of sine, which is negative cosine of x. We do it all again. Now, let's be extra careful here. We still have the x squared times sine of x. And now we have minus 2 times the entire integral of x sine of x. So that negative 2 gets multiplied by the entire ultraviolet super voodoo. So it gets multiplied by x times negative cosine of x minus the integral of negative cosine of x dx. Now, I am a fan of making my life easier. So if I was dealing with this, I would probably do the following. I would say, okay, this is x squared sine of x. Minus 2 times x times minus cosine is a plus 2x cosine of x. And minus 2 times minus 1 times minus, that's going to be a minus 2 integral of cosine of x. And then we still need to do the integral. So finally, we get x squared sine of x plus 2x times cosine of x minus 2 times the integral of cosine of x is positive sine of x plus c. Ooh, that's a lot. Questions about anything we've done here? I'm afraid that this table is just too small. Sorry, it's fine. Yeah. Oh, no, not questions. Like, okay. Like, no questions. Okay. So let's see, which way do I want to go next here? We could do that. Yeah. Let's talk about. Yeah. But what if we had to do the integral? Yeah, we'll do it, of x cubed e to the negative 2x dx. So we're gonna do this one, even though it's gonna be terrible. And then I'm gonna show you a trick. Because there's a great trick that your teacher may or may not teach you. It's still worth knowing even if you don't learn it in class. So yeah. So looking at the late again. Let's see. I don't have a logarithm. So u is going to be the any power of x. Some people call it the algebraic term. So our u is going to equal x cubed. Our du is 3x squared. Our dv is e to the negative 2x dx, or the rest. I think it's also not bad to label these things. Right, there's u, there's everything else, which has to be dv. And then your v, okay, I want all of you on your own to find the antiderivative of e to the negative 2x as quickly as you can. I'll remind you, you're not going to end up multiplying by negative 2. You're going to be doing something else instead. You should get e to the negative 2x divided by negative 2. That's your dv here. And the thing is, we're going to have to do that a bunch of times. So that's why it's important to be able to do it quickly. In case you're not comfortable with that, let me remind everybody, the reason I don't want to take up that room over there. Fine, I'll take up that room over there. The reason that that's easy-ish to see is that if you take the derivative of 1 over negative 2, a constant, times e to the negative 2x, you get 1 over negative 2 times the derivative of the negative 2x, which is e to the negative 2x times negative 2. And the negative 2 and the negative 1/2 cancel, and you just get e to the negative 2x. So the derivative of e to the negative 2x divided by negative 2 is e to the negative 2x. And the antiderivative of e to the negative 2x is negative e to the negative 2x divided by negative 2. But the general rule here is just that if you're anti-differentiating e to the blank times x, you get e to the blank times x divided by blank. So more generally, the antiderivative of e to the a times x is e to the a times x divided by a. A good rule to know. You could, although I don't want you to, but you could do a u sub here. Or you could do u equals negative 2 times x and then d, right? But you're already having to do a bunch of other stuff in this problem. That's why we're trying to not take forever to do that part. Okay, so now we're going to write the ultraviolet super voodoo. So u times v, x cubed times e to the negative 2x over negative 2 minus the integral of v du. Oh, I forgot my dx there, sorry. So that's going to be e to the negative 2x divided by negative 2 times 3x squared dx. And as you might notice, this is going to require integration by parts again. And again. So here's something to know. If you have x to a power times e to the x, or times cosine of x, or times sine of x, the power that's on x is the number of times you will have to do integration by parts. So this was like x to the 4th times sine of 2x. You'd have to do integration by parts 4 times. That's kind of terrible. Thankfully, there's a shortcut. But we're going to do it the long way one more time just to feel the pain before we get to do it the easy way. Plus, some teachers are not super cool with the other shortcut method I'm going to show you, but that doesn't mean it's not a valid thing to know. So I'm going to look at this. I'm going to rewrite this as, I'm going to write it as negative 1/2 x cubed e to the minus 2x. Minus a minus becomes a plus, right? That's a minus 1/2 there. There's a 3 there. So I'm going to make this a plus 3/2 integral of x squared e to the negative 2x dx. Just simplifying it a bit, trying to get rid of any repeated negative signs when I can. And then we're going to do another integration by parts. Now u is going to equal x squared. dv is going to be the same as it was before, e to the negative 2x dx. du is going to be 2x dx. v is going to be e to the negative 2x divided by negative 2. So typically with typically with these problems where your u is equal to x to a power, every time you do integration by parts, the power decreases by 1 because you end up getting the integral of your dv or your v times du. And so your du has a 1 less power than your u had. Okay, it's the same old thing once again. Negative 1/2 x cubed e to the negative 2x plus I've got 3/2 times the whole thing here times my new u times v. So x squared times e to the negative 2x over negative 2 minus the integral of v du e to the negative 2x over negative 2 times 2x dx. And yes, I should simplify. And I do think we should simplify as we go here just to make our lives easier. So we got negative 1/2 x cubed e to the negative 2x. I'm going to distribute the 3. Am I going to distribute 3/2? That seems dicey. I'm going to wait on that. Let's leave that 3/2 out there. I've got a negative 1/2 x squared e to the minus 2x. And minus a minus becomes plus, and the 2 here and the 2 here cancel out. So I really just got x e to the negative 2x dx. One more time. So now for this integral here, we're going to let u equal x. dv once again is e to the negative 2x dx. du is just 1 times dx. And v is once again e to the negative 2x divided by negative 2. So we've got negative 1/2 x cubed e to the negative 2x plus 3/2 times negative 1/2 x squared e to the minus 2x plus finally the integral of this is going to be uv. So x times e to the negative 2x divided by negative 2 minus the integral of v du, which is negative 1/2 e to the negative 2x dx. Wow, we're still not quite done, right? We still have to finish this off. But at least we're finally at the stage where this can actually be integrated. We can actually integrate e to the negative 2x. Okay. So I'm going to try and wrap this up in one step because it's a lot of writing. So a negative 1/2 x cubed e to the negative 2x. Distributing the 3/2, 3/2 times negative 1/2 is minus 3/4 times x squared e to the negative 2x. 3/2 times minus 1/2 is another minus 3/4 times x e to the negative 2x. And finally, let's think this through here. So a minus is going to be a plus. So it's going to be plus. I'm going to have 3/2. And then the integral of this is going to be, I might need another. No, I don't want to write another step. So I've got, right, I dealt with the minus, the plus. And the integral of 1/2 e to the negative 2x is 1/2 e to the negative 2x divided by negative 2. Yes, I'm aware I could do some simplifying there, but I really don't want to. And we could see, that'd be negative 3/8 times e to the negative 2x if you really wanted to simplify that. So I hope you all can see that's a giant pain, right? This is terrible. So let me show you a faster way of doing problems that specifically fall into one of 3 categories. So if your integral, and I'm going to write this kind of so I used to write it like this. So if you have the following sort of integral, sorry, I was trying to not to cover up the stuff I had there, but I totally covered it up. Yeah, you can still see that kind of, yeah, that's kind of, yeah, okay. So if you have the integral of x to the n times sine, really it can be something times x, doesn't have to be just sine of x, or the integral of x to the n times cosine of something times x, or the integral of x to the n times e to something times x. And really I should say, it doesn't have to be x to the n, you can really have a polynomial. You can have like x to the 3rd plus 5x squared plus 2x, right? It can be more complicated. So really, we can have a polynomial instead of just x to the n. But if we have something like this, we can use this method. It's really just a shortcut. It's kind of like, did any of you ever learn, well, I imagine all of you have at some point in your life seen polynomial long division. Yes. Have any of you ever learned synthetic division? It's okay if you haven't. It's not my favorite thing ever. It has its uses, but it's kind of the same thing here. Synthetic division is just a shortcut for polynomial long division. Here we're going to be learning a shortcut for these three integrals, which is called the tabular method. Because you're making a table. That's why it's called the tabular method. So let's actually look at this. Let's look at the previous, not this one we just did, but the one before that, which was, I forgot what it was because I put it away. It was x squared times cosine of x. So here's how the tabular method works for x to a power times either cosine or sine or e to the x. This does not work for any other type of integral. I want to be super clear about this. It only works for an integral where your choice for u, if you kept taking its derivative, would eventually be 0, which is only true if you have x to a positive integer power. And your choice for dv is something that when you integrate it, it keeps just cycling through the same sort of thing. And the only functions that really cycle when you integrate them are sine, cosine, and e to the x. Anything else, when you integrate it, gets more complicated typically. But sine and cosine, they just go back and forth between sine, cosine, negative cosine, et cetera, et cetera, et cetera. And e to the x is just e to the x, e to the x, e to the x. So these are safe choices. All right, so check this out. If we were doing integration by parts here, which we are, we would make the choice that u was equal to x squared and dv was equal to cosine of x dx. But instead of writing out like this, we're going to make a little table. So over here, we're going to be like, okay, u and dv. And in our u table, we'll start with our first thing. And then below it, we want all of the derivatives of that function. So we just keep differentiating. So the derivative of x squared is, and the derivative of 2x is, and the derivative of 2 is, and then we got to 0, so we stop. And then in our other column, in our dv column, we're going to find all the antiderivatives until we get to the same number of entries. So we're going to start with cosine of x. And then we're going to anti-differentiate and get positive sine of x. And then we're going to anti-differentiate and get negative cosine of x. Then we're going to anti-differentiate and get negative sine of x. So just to be super, super, super clear, going this way, we are taking derivatives. Going this way, we're taking anti-derivatives. Okay, here's the final step. Take this thing up here and multiply it by that thing there. Same there, same there. But we're going to add x squared times sine of x, subtract 2x times negative cosine x, add 2 times negative sine of x. It's always plus minus plus minus plus minus plus minus until you run out of arrows. It's always start to the plus, and then you just go plus minus plus minus plus minus. All right. So then here's what we've got. Our integral of x squared cosine of x dx is equal to plus x squared times sine of x minus 2x times negative cosine of x. Yes, I would fix that. Plus 2 times negative sine of x plus c, which if we write it more nicely is x squared times sine of x plus 2x times cosine of x minus 2 times sine of x plus c. Which if we look back at our previous work, hopefully it's the same. Yep, looks pretty stellar. It's the same. So this is a shortcut for having to do repeated integration by parts for only these types of integrals. It does not work for any other type of integral. But if you see something like, for example, if on your homework you had to do the integral of x cubed e to the negative 2x, instead of doing all the terrible 3 integration by parts we just did, you can say, okay, the integral of x cubed e to the negative 2x dx, our u would be x cubed. Our dv would be e to the negative 2x. And then we make our table. We're going to start differentiating. So derivative of x cubed is 3x squared. Derivative that's 6x. Derivative that's 6. Derivative that's 0. And then we do the same number here. So every time we integrate e to the negative 2x, we're going to divide by another negative 2. So the first antiderivative here is e to the negative 2x divided by negative 2. And the next one's going to be e to the negative 2x divided by negative 2 times negative 2, which is positive 4. And the next one's going to be e to the negative 2x divided by negative 2 times negative 2 times negative 2, which is negative 8. And then finally, e to the negative 2x divided by positive 16. And then it's a, oops, it's a plus. I like to switch colors here. And then a minus, and then a plus, and then a minus. Now, I should say the plus minus is not the overall sign. It's just saying that it's plus that times that, minus that times that, plus that times that, minus that times that. So you still have to be aware of the other signs that are in there. So this is going to end up equaling, I want to write it down here so I have room. So the integral of x cubed e to the negative 2x dx is going to equal x cubed times e to the negative 2x over 2. Sorry, over negative 2 minus 3x squared times e to the negative 2x over 4 plus 6x times e to the negative 2x over negative 8 minus 6 times e to the negative 2x over 16 plus c. And what you can see here is that all these things happen to turn out to be negative. Not that that really matters, but if we simplify this, we get negative x cubed e to the negative 2x over 2 minus 3/4 x squared e to the negative 2x minus 3/4 x e to the negative 2x minus 3/8. Yeah, I can say eighths, sure, e to the negative 2x plus c. Which, if we look back at our previous work, I mean, it's not, it doesn't look, yeah, no, it's the same. Yeah. 3/2 times 1/2 times negative 1/2 is negative 3/8. It's the same. So totally works. Kind of cool. It's a useful thing to know. Okay. Let's see. What else have we got here? Yeah, stuff. So I would certainly recommend using that if you have to. Let's look at something else, which is, yeah, we better look at some too. Well, I was looking at your homework. I want to see if there's anything crazy from your homework, but I forgot where I put it. So all right, so what about something like this? The integral of e to the 3x times sine of 2x. All right, well, let's go back to the drawing board. I don't have a logarithm. Oh, wait, let's fine. We can go back. We'll do this one. That's fine. Don't have a logarithm. Don't have a power of x. Right. I don't have x to the third just on its own, or x squared, or x to the first on its own. But I definitely do have powers of x, but they're in other functions. So it's not like I really have just a power of x. So trig is my choice for u. So I'm going to let u equal the trig thing. And I'm going to let dv equal the rest. Something to know about this, technically, you can make the opposite choice. You could let u equal the e to the x thing and dv equal the trig thing. Either, it doesn't really matter which order you do it as long as you're consistent. So I know I've said you should do it this way, and I would encourage you to do it this way because I feel like it's easier. Yeah, yes, sure, yeah. But yeah, either way, actually, you'll see what I mean in a second. So du, oh, I gotta use some chain rule. Sine of 2x is cosine of 2x times 2 dx. And antiderivative of 3x is e to the 3x divided by 3. So here's what we're gonna get. We're gonna get that the integral of e to the 3x times sine of 2x dx is equal to uv, so it's going to be sine of 2x times e to the 3x over 3 minus the integral of v du, which is e to the 3x divided by 3 times cosine of 2x times 2 dx. I'm going to simplify a tiny bit. This is equal to 1/3 sine of 2x e to the 3x. I'm going to bring out the 2/3 to write this as minus 2/3 integral of e to the 3x cosine of 2x. And what you might recognize here is that we're kind of back in the same situation we were in before. We still have an e to the 3x times a trig function of 2x. It just happens to be cosine, not sine. Now, here's where we have to be super duper careful about what we do next. Whatever you've done the first time, you have to make the same type of choice the second time. So if I've chosen u to be my trig thing and dv to be the rest, I again need to choose u to be the trig thing and dv to be the rest. If you make the opposite choice, you'll actually end up undoing all the work you've done, and you'll end up getting that the integral of e to the 3x times sine of 2x is equal to the integral of e to the 3x times sine of 2x, which is totally true and totally not helpful, because yeah, of course the integral is equal to the integral. But you haven't gotten anywhere. So we definitely have to make the choice here that u is equal to cosine of 2x and dv is e to the 3x. So cosine 2x, oh sorry, yeah, that's right. And dv is equal to e to the 3x dx. So now my du is negative sine of 2x times 2 times dx. My v once again is e to the 3x over 3. Okay, so check this out. I am going to very specifically write the entire equation. So I'm going to write the integral of e to the 3x times sine of 2x dx equal to this 1/3 sine of 2x e to the 3x minus 2/3 times my ultraviolet super voodoo. Right, I'm doing the integral of this. This is my u, this is my dv. I'm going to get uv minus integral of v du, so it's going to be uv, so cosine of 2x times e to the 3x over 3 minus the integral of v du, which is e to the 3x over 3 times a negative sine of 2x times 2 dx. Now here's what we should be making note of. The integral that we're trying to find showed back up again. So here's what we're going to do. We're going to simplify this a tiny bit. We're going to say the integral of e to the 3x sine of 2x dx is equal to, let's see what we've got here. 1/3 sine of 2x times e to the 3x minus 2/3 times 1/3 is minus 2/9 times cosine of 2x times e to the 3x. And minus 2/3 times another minus 2/3 is going to be a minus 4/9 integral of e to the 3x times sine of 2x. Let's make sure we're all on board with that. This is a negative 2/3 times a -1 times a negative 2/3, which is a negative overall, and it's a positive. Yeah, it's a negative 4/9. Okay. But now look, I've got this integral and 4/9 of that integral, and I can add that over there. So if I've got 1 of a thing plus 4/9 of a thing, 1 plus 4/9 is 13/9. So if I add this over here, I end up having 13/9 times my integral equal to 1/3 times sine of 2x times e to the 3x minus 2/9 times cosine of 2x times e to the 3x. And of course, I've run out of room at the last possible moment here. So then finally, solving for my integral, I just multiply both sides by 9/13. So I can say that my integral of e to the 3x times sine of 2x is equal to 9/13 times all that. 1/3 sine of 2x times e to the 3x minus 2/9 cosine of 2x times e to the 3x, and then slap on a plus c. If you wanted to simplify this, there are 2 things you could do. You could factor out e to the 3x, which I think is not a bad idea. If I could keep it up here, okay, sure. So we could rewrite this as e to the 3x times, and then we could distribute the 9/13 in. 9/13 times 1/3 is 3/13 sine of 2x, and 9/13 times 2/9 is going to be 2/13 cosine of 2x. I'm not writing the e to the 3x's because I factor them out. That's probably a more typical way of writing this answer. So, kind of a lot. But the point here is that if you see, and there definitely is, I think this is the last problem in your 6.2 homework assignment. There's one exactly like this, where it's an e to the something times x. If I don't remember what it is, I can't find it. And either times a sine or a cosine. And so you'll do this process where you have to do integration by parts twice. You'll end up with the same integral at the end, time like some multiple same integral at the end. You'll add that over to the other side and then multiply both sides by whatever the reciprocal of that is to get rid of that. So you can just get this integral we're trying to find all by itself. It's kind of neat. It feels kind of like you're cheating. Like it kind of feels like you didn't really like do the integral because you just did this thing twice and then, oh, well, do some algebra, bring it over here and oh, you got the thing. But it really is what the integral is. It's kind of neat. Questions about this one? Look at something not quite as complicated. Although you might disagree with me. Oh, so yes, Zara, but I want to do one more thing. And then if you can actually be a little bit more specific about what you're asking for, I'm happy to do it. I'm just not quite sure what you mean. So if you could clarify in the chat, I'd appreciate it. Well, let's do one other important integral, which I will preface with this problem. So let's say I want to find the integral of the natural log of x to the 8th. I mean, I guess I could think about a u sub, but I don't think it's going to work. I mean, I could try letting u equal x to the 8th, but it seems not likely. Because if I let u equal x to the 8th, my du is 8x to the 7th dx, and that's not good. That seems not great at all. So probably not going to work, right? If you see that dx equaling du over 8x to the 7th, if you plug that in, you're going to have this x to the 7th in the bottom, which you can't really do anything with. That's a problem. So I'm not going to go that way. It's probably not a u sub. So but I don't really have a mixture.
So if you did do it that way, then why couldn't you just plug it and do the thing where you plug in the u for x?
That's a good question. Let's take a look, because that's a fair point. So let's say I did do that. So I said, all right, I've got the natural log of x to the 8th is u, and dx is du over 8x to the 7th. Okay. So then I am trying to do a back sub here. So if I take my u equals x to the 8th and solve for x is going to be the 8th root of u, or u to the 1/8 power. So then I can plug that in over here, and I'll have the integral of the natural log of u times du over 8 times u to the 1/8 to the 7th is to the 7/8 power. So we could rewrite this as the integral, let's say 1/8, and then you have a natural log of u over u to the 7/8 power. And then you totally could do integration by parts. It's unfortunate we already used the letter u. So here's what I would say. Not that I haven't seen any of these on your homework, but if you encounter a situation where you have to do a u sub and then integration by parts, I think it's a good idea to try to, if you see that that's going to happen, to not use u first. Like do a t substitution instead of a u substitution. Here, if I was going to do integration by parts, I would let w instead of u equal u to the negative 7/8. Oh, no, that's not the right choice. I'm not obeying my acronym. I should not do it this way, really, is the real answer. But the point is, you could do it this way, but to do it this way, you'd eventually have to use integration by parts. So if you're doing a u sub that looks wild, and then you're getting to integration by parts, there's a good chance that you could have just done integration by parts from the get-go. But here, if you really, really wanted to, you would let w, your u, be the natural log of u, and your dv would be u to the negative 7/8. And then it would totally work. It'd be terrible. Here's what you should do instead. So whenever you have the natural log of x to a power, it is often a good idea to try simplifying it first. Meaning instead of doing the integral of the natural log of x to the eighth, let's do the integral of 8 times the natural log of x dx, which is just 8 times the integral of the natural log of x. So I should point out the integral of the natural log of x is kind of the one exception that we're going to encounter to the it needs to be a mixture rule. Technically, it's a mixture. It's just so I have a logarithm and I have a power of x. And the power of x is x to the 0th, which feels kind of like cheating, but it's what we've got. So here, this is integration by parts. And the choices we're going to make, well, we always pick u to be what if we have it? Are we on time or are we late? We're late. Right. We pick u to be the log. You should ask, right? I was late today. You should ask, is James always on time or is he sometimes late? Oh, he's sometimes late. Oh, late. Yeah, log. Yeah. Okay. So u is the natural log of x. And this is actually a really good time to say, instead of dv being, whatever, dv is just the everything else, the rest. Exactly. So in this case, what does that leave us with? Just dx. So then our du is 1 over x dx. And our v, the antiderivative of just 1, is x. And then we can do the ultraviolet superposition. So the integral of the natural log of x is equal to u times v, so x times natural log of x, minus the integral of v times du, x times 1 over x times dx. And this again is the case where you definitely should simplify the integrands here. So this is equal to x times the natural log of x minus the integral of x times 1 over x is just 1 dx. And the integral of 1 is just x. So we get x natural log of x minus x plus c. And that is the antiderivative of the natural log of x. It's cool. So now you know the antiderivative of the natural log of x. It probably isn't something you need to memorize, but it certainly has helped me having memorized it in the past, just being able to spit it out instead of having to go through this process every time. So back to the question that we were actually doing, the integral of the natural log of x to the 8th is 8 times the integral of the natural log of x, which is going to be 8 times x natural log of x minus x plus c. I will once again point out that our natural log does not have an absolute value because we never actually integrated 1 over x. You only get the absolute value if you do the antiderivative of 1 over x equals the natural log of the absolute value of x. I just want to make sure that's super clear. Okay. Oh, sure. So actually, oh, definitely. Oh, sure. Yeah, okay. So Zara asked me to look at something like question 9 from section 6.2. Yeah, totally. And I'm going to make it really extra terrible. It's a can. So definite integral. So let's say we have the definite integral, the integral from, let's make it terrible, from 0 to 6 of x to the 4th over e to the x. Wow, looks terrible. Here are my words of advice for definite integrals with integration by parts. Do the indefinite integral first. I don't actually want to write out all the stuff with the limits of integration the whole time. So first, I'm just going to deal with the indefinite integral. So I'm going to do the integral, and instead of x to the 4th divided by e to the x, I really should be thinking of this as x to the 4th times e to the negative x. All right. So this is one of my 3 special types of integrals where I could do integration by parts how many times? 4 times? No, I shouldn't do it 4 times. I can do tabular integration here. And definitely I would encourage you on your problem 9 on this homework on the section 6.2, I would encourage you to use tabular. So I'm going to let u equal x to the 4th and dv is going to be the rest, except I'm not writing the dx because I'm not. So the derivatives here are 4x cubed, 12x squared, 24x, 24, and yes, we do need the 0. My antiderivatives here are the antiderivative e to the negative x is e to the negative x divided by -1, but divided by -1 is multiplied by -1. So the antiderivative here is negative e to the negative x, and then the antiderivative of that is positive e to the negative x, and the negative e to the negative x, positive e to the negative x, negative e to the negative x. Don't fool yourself here. I didn't take derivatives to get all these. I took antiderivatives. They just happen to be the same for this particular function. But it's always antiderivatives this way on this side and regular derivatives on this side. Just make sure you're aware of that. Just like you would usually do for your u and your dv. You would take the derivative of u to get du, and you would take the antiderivative of dv to get v. All right, so this is going to equal, all right, plus, minus, plus, minus, plus. Checking this out, it looks like everything's going to be negative. Because it's going to be plus x to the 4th times negative e to the negative x minus 4x cubed e to the negative, right? All of them are going to end with a minus sign in front. So we can be kind of judicious about that. We're going to get a negative x to the 4th e to the negative x minus 4x cubed e to the negative x minus 12x squared e to the negative x. I should just factor out the e to the negative x. Minus 24x e to the negative x. And finally, minus 24 e to the negative x. And I don't need to write the plus c because this is what actually the problem I was dealing with. So now I suppose I could just, instead of, since I was very lucky here and I didn't have to write out a bunch of work, I didn't really do this extra step. So here's what I would say. If you're doing like integration by parts and you've got some stuff to work through, you don't want to carry these limits of integration with you through the whole process because it's just kind of one more thing to keep track of. So what I would say is if you have a definite integral, do the integral, find the antiderivative, and then afterwards be like, okay, then I'm going to say that the integral from 0 to 6 of x to the 4th e to the negative x dx. I really would have just done it right here, but I'm trying to show you what I do. Is all this stuff. Again, let's factor out the e to the negative x because we can. Let's factor out the negative e to the negative x. So after x to the 4th plus 4x cubed plus 12x squared plus 24x plus 24 from 0 to 6. And then you just plug it in 6 and you're getting negative e to the negative 6 times, oh boy, plug it in 6. Okay. Let's just be smart. Let's say that's 6 to the 4th plus 4 times 6 cubed plus 12 times 6 squared. I know that's 36 plus 24 times 6 plus 24 minus, then we plug in 0 and we get negative e to the 0 times 0 plus 0 plus 0 plus 0 plus 24. Which I guess I could have fit in over there. Let's put it, so that's going to be minus a minus 24. Because e to the 0 is just 1. So put that right there. So that problem number 9 isn't too terrible if you utilize tabular integration. If you don't, it's pretty awful. But again, I would say even if you don't, you should still do all of your integration, anti-differentiation just without as an indefinite integral, and then at the very end be like, okay, then I'm going to plug in 0 and 5, 0 and 6, whatever your numbers are. All right, that's all we got time for today. I'll be over in CADS when they get over there. Have a lovely weekend. When you guys have your next test? Okay. The 18th, so 2 weeks from today. Okay. You guys do anything on the evening? Welcome, Zara.